So, good day everyone. I'm Marjorie Ganyola from BS Edma 3B. Now we will be exploring about the different subgroups formed from our table M, which was showed on the previous video. So here's our table M, and we have proved that the table M that represent the M double square algebra or our geometric model forms a group structure because it is closed, it is associative, it has an identity element, and each element has a unique inverse. So now we're going to explore naman is various subgroups. So we're going to talk about the improper subgroup, proper subgroup, and the trivial subgroup. Improper subgroup is the group itself, while proper subgroups naman are all of the possible subgroups that we can form from the original group, but not equal to the whole group. While trivial subgroup is the subgroup that consists only the identity element. So here's our improper subgroup. As you can see, it only consists itself or the group itself, and our proper subgroups. Actually, we have 17 of them, and here they are. And later on, we're going to verify if these subgroups satisfy the condition of being a subgroup. Lastly, we have this trivial subgroup. As you can see, it only consists the identity element as what I've said earlier. So at this very moment, we're going to verify if this subgroup satisfy the conditions of being a subgroup. So we have three. First, it is a subset of the group table M. It is group, and lastly, it has the same binary operation star as the group M. So improper subgroup is already a group, so it already satisfies one of the conditions. So improper subgroup contains the group itself, so it is also a subset of M, and it has the same binary operation as the group M because it's just itself. So improper subgroup satisfies all of the conditions of a subgroup. So now we have the M sub 1. Let's see if this satisfies the condition of a subgroup. So as you can see, M sub 1 is a subset of M because A, J, E, O, 8, 5, 9, and 2 are all came from the original group M. It is a group. So to check if it is a group, we must satisfy its condition. First is closed. So as you can see, this table is closed under the elements of A sub 1. All of the elements here are all here. Walang nag-overlap. Next, to see if it is associative, we have to check and flip 180 degrees. And then if we interchange rows and columns, the elements inside will be back from the original figure of the table. Therefore, it is associative. It also has an identity element, which is A, and the inverse element exists for all because the inverse element of A is A, J is O, E is E, O is J, 8 is 8, 5 is 5, 9 is 9, and 2 is 2. Also, M sub 1 has the same binary operation star as M, so it is indeed a subgroup of M. Next is M sub 2. Let's see if this satisfies the condition of a subgroup. M sub 2 is a subset of M, and it is a subset of M because A, J, E, O, I, 1, 6, 4, and 3 are all came from the group M. M sub 2 is a group. It is correct because all of the elements are closed under A, J, E, O, 1, 6, 4, and 3. Next is to check if it is associative, we have to flip it 180 degrees and interchange rows and columns. And if we did so, the table or the elements inside will still look like the same as the original. So it is indeed associative. So the identity exists in this table also because A is the identity element. Therefore, the inverse exists also for all of the elements. The inverse of A is A, J is O, E is E, O is J, I1 is 1, 6 is 6, 4 is 4, and 3 is 3. Also, this subgroup has the same binary operation as the group M. Therefore, M sub 2 is indeed a subgroup of M. Next is we also have here M sub 3. and it has an order of 8. So M sub 3, let's see if it satisfies the condition of being a subgroup. M sub 3 is a subset of M because A, M, J, I, E, G, O, R are indeed came from the group M. It is a group. So let's see if it is a group. It is closed. So as you can see, all of the elements here are closed under the elements of M sub 3. To check if it is associative, we're going to flip it 180 degrees. And if we interchange rows and columns, the table or the elements will still look like the same as the original. So it is indeed associative. It also has an identity element, which is A, and the inverse element exists for all. Also, to satisfy the last condition, M sub 3 has the same binary operation star as the group M. So M sub 3 is indeed a subgroup of M. Now let's move to the subgroup with an order of 4 or 4 elements. So M sub 4. Does this satisfy the condition of a subgroup? Let's see. M sub 4 is a subset of M. It is correct because A, J, E, O came from the original group M. Is this a group? So let's see if it is a group. It is this form a closure. Yes, because all of the elements in the table are closed under A, J, E, and O. Is this associative? So to check if it is associative, we're going to flip the table 180 degrees and interchange the rows and columns. So there we go. So the table or the elements inside will still look like the same as the original. So it is indeed associative. It also has an identity element, which is A. And the inverse element exists for all because the inverse of A is A, the inverse of J is O, while the inverse of E is A. The inverse of I yes, O. The inverse of E is E pala, while the inverse of O is J. So also M sub 4 satisfies the last condition, which is having the same binary operation star as M. So M sub 4 is indeed a subgroup of M. Next is M sub 5. Since M sub 5 is isomorphic to M sub 4, it is also a subset of M. It is a group because it is closed. It is associative because if we flip the table 180 degrees and interchange the rows and columns, we can still end up by looking the table the same as the original. Yeah. It also has an identity element and inverse element exists for all. Also, M sub 5 has the same binary operation as the group M, so it is indeed a subgroup of M. M sub 6 is also isomorphic to M sub 4 and M sub 5, so it is indeed a subset of M. It is a group because it is closed. As you can see, the elements inside the table is closed under the elements of M sub 6. It is associative because if we flip the table 180 degrees and interchange the elements, I interchange the columns and rows, we the table or the elements inside will still look like the same as the original. So it is indeed associative. It also has an identity element and the inverse element exists for all. Also, the M sub 6 satisfies the condition of having a same binary operation star as the M. So M sub 6 is also indeed a subgroup of M. Next is M sub 7. It is also isomorphic to M sub 4, 5, and 6. So it is indeed a subset of M. M sub 7 is a group because it is closed. It is also associative because if we flip the table 180 degrees and interchange the element ID rows and columns, we the table or the elements inside will still look like the same as the original, so it is associative. It also has an identity element, A, and the inverse element exists for all. And also it has the same binary operation star as the group M, so it is indeed a subgroup of M. We have here the last order 4 subgroup. So it is also isomorphic to on M sub 4, 5, 6, and 7. So it is indeed a subset of M. It is also a group because it is closed. It is associative because if we flip it 180 degrees and interchange the rows and columns, we can still end up to the original figure of the table. So it is associative. It also has an identity element, which is A, and the inverse element exists for all. Or so, M sub 8 has the same binary operation as the group table M. So it is indeed a subgroup of M because it satisfies all of the conditions. Next is the uh, subgroups with order 2 or 2 elements. So we have 9 of them, and here they are. As you can see, they are all isomorphic. All of them have the same image. So it is easy for us to find if they all satisfy the condition of a subgroup. So they are all a subset of M. So it is correct because since all of those elements came from the group M, all are grouped. So to satisfy this, we have to check if it is closed. So as you can see, all of them are closed. Lahat na nasa table is closed under on what subgroups are they belong to. It is to check if it is associative. And if we're going to flip them 180 degrees and interchange the rows and column, we can still get the original figure of the tables. So it is indeed associative. They also has an identity element, which is A, and the inverse in all of those tables also exists. Therefore, all of these tables are grouped. Now, the last condition that we're going to satisfy is if they have the same binary operation as the original group table M. So as you can see, we have here star and it is the same as the group M. So all of these, all of these subgroups with order 2 are all a subgroup of the group M. So lastly, we have here the M sub 18 or the what we call the trivial subgroup. As you can see, it only consists one element, which is the identity element. So this is already considered a group because it satisfies all of the group actions, which are the closure, associativity, identity, and the inverse. This table shows that when the operation is performed on A, this is the A, if we perform it by itself, the result is still A, which is the identity element. So this is also a group. It also has the same binary operation star as the group M. Also, M sub 18 with one element A is also a subset of M. So this is indeed a subgroup of the group M. Here's our lattice diagram that connects all of our subgroups. We started from the improper subgroup or the group itself, followed by M sub 1, M sub 2, and M sub 3, who has an order of 8, this, and then M sub 4, M sub 5, M sub 6, M sub 7, and M sub 8 with an order 4. And then the other 9 subgroups are all here with an order 2. And lastly, the M sub 18 or the identity element that connects all of them are here at the bottom. So that is all. Thank you so much. Again, I am Marjorie Gagnola from BSEd Math 3D.